I'm going to talk about the future. And you're lucky to be here. And trust me, in 3 years, you're going to talk to your friends about this talk, about this session, because you are here to hear the future. Now, has anyone heard about KV? How many of you have heard about KV cache recently and wonder what it is? Okay, this is a talk for you, and you have a great intuition that this is going to be the future, even though you don't know much about it. All right, so a few words about myself. I've been doing research in the University of Chicago. Formerly, I'm a professor, and I led my research team. And 3 years ago, we have this epiphany that KV cache, which I will introduce in a few minutes, is going to be the future of the internet. The future data for the future internet, because that's what the model can understand right away. Now, we started writing first papers in various topics, and then we open sourced this project called LMCache. It's the first open source library in industry to help people manage and store KV cache. And then a year ago, we started this company called Tensormesh to commercialize the best techniques we have. Now, for most of you who don't know what KV cache is, here's a 1-minute version. Okay? First of all, everything you heard about KV cache is true. Okay? KV cache can save you cost. KV cache can make things more scalable. KV cache reduce the delay. KV cache does amazing things. But how does it do that? The key of KV cache is it avoids repetitive computation. It cache model internal state. Now, that, again, I would say is the basic understanding of what KV cache is. But that's a good start. So let's start with what large language model does, and essentially a transformer does. A transformer will process a bunch of input tokens through multiple layers. And each layer has this thing called QKV multiplication. It's the attention mechanism. And the attention mechanism essentially is the bottleneck of all LLM inference. An attention mechanism is basically a 3-matrix multiplication. It's a Q matrix by K matrix by V matrix. It's very expensive. It's quadratic to the length of the input tokens. Now, that's bad, but once you realize most of the tokens in the input are reusable, and reusable across different iterations with the same query, and also reusable across queries. Think about you ask multiple times, you ask multiple questions about the same document. That document's tokens will be there in the input multiple times. And in a multi-term agentic environment, all this context accumulated by the model over time will be there in the input. So there are a lot of reused tokens. And if you realize there are reused tokens, most part of the QKV matrix will be reusable. So you can mask all the KV, the part of the QKVs that you have seen before, and then this complexity all of a sudden drop down from quadratic to linear. That is something transformer researchers has known for almost a decade now. Okay, so if you have K and V matrices stored in the GPU memory, that saves a lot of compute for you, both within a query and across queries, across different inference queries. Now, there's a general trend in industry that, in industry and academia, that people are paying more and more attention to KV cache. And this is no longer viewed as a byproduct of inference engines anymore. It's an AI native data super valuable in its own right. In industry, people are trying to store more KV cache because it can save compute cycles for you. In academia, people are proposing more and more research ideas around this KV cache data to improve the efficiency and quality of inference engines. Now, this talk, we're going to talk about these two sides and then talk about the project that enables these two to converge. But what's important here is industry and academia are looking at this problem, are looking at this interesting data structure in a very different perspective. Okay? And LMCache, the open source project, and also what our company is trying to build the best infrastructure to enable both industry and academia to apply their best ideas. Okay, so let's start from how industry look at this problem. What's the industry perspective for KV cache? Now, first of all, you have to realize KV cache is not a small data. It's a huge amount of data. Okay, Now, just to give you a sense how big the data is, let's imagine not the latest AMD GPU, I say. One MI300X GPU from NVIDIA. No, sorry, AMD. Shoot. So AMD per day. So let's say for 24 hours, how much KV cache can be generated by this MI300 GPU for 24? I don't know why, but anyway, it gives the answer. So the idea is there's a lot of data created by a single GPU in 24 hours. What does that mean? That means you need to store them somewhere, or you have to discard them, because GPU memory is never going to be that big. Now, the question here is why you should store that much KV cache. Why? Well, industry want to store this KV cache because it saves money, right? If you skip a lot of compute, you save a lot of money. The more you reuse KV cache, the more you save. Now, let's make some assumption. Assuming a big model, this is actually Q13 model running on 8 GPU nodes, $2 per GPU per hour. This is typical pricing. Now, you can trade the GPU cycles by storing more KV cache in storage. Now, on cloud, typical S3 Express pricing would be like a 1 terabyte storage to 15 cents per hour. Now, if you store more KV cache on storage and try to reuse them, the question is, how much KV? When will be the break-even point, right? If you store more KV cache, incur more storage, and even though you save GPU cycles, when will be the break-even point? So essentially, I'm asking how frequently you need to reuse the stored KV cache in order to break even. Now, if you do the math, actually, it's very hard to do the math, but we did it for you. About 1% reuse rate, essentially like 2-3 times per week, will be enough to break even the cost. That's surprising because in our trace analysis, most times, at least 10% of queries will have that kind of property. Will be reused more than 3 times per week. Okay? So there's a lot of KV cache to be stored and to save your cost. Now, of course, if you increase the average hit rate to 10%, that's even more amazing because you save more money. How much can you save? Well, assuming a 1,000 node, the GPU cost is still going to be about 30-ish million, but the storage cost is just 4 million, which means you save a lot. You save 29 million on a 1,000 node deployment of this setup. Now, there's a lot of money to be saved, and that's why industry gets so excited about this. Now, in practice, people do store KV cache outside of GPU memory. Here is an example of deployment by a customer of LMCache and VLM. They put this system in place for 5 weeks, and this is a KV cache handled by LMCache library for the first 5 weeks. You can see there are more and more KV cache to be stored. Okay, that's amazing, but even more amazing is most of these KV cache do not stay in GPU memory after the query is done. Now, where to store them? Of course, right? We have been in the front seat row to watch the growth of KV cache, first from GPU memory only to CPU memory to SSD or CPU memory pooling, and then these days it's all, people even start to store this in S3 buckets or Redis even, Redis Cloud. So what are the challenges here facing industry? Of course, you don't want to buy too much CPU memory or SSD either, because these guys are these things are having higher and higher prices these days. So how to fit more KV cache, and at the same time, how to move these KV cache back into GPU memory, because in order to reuse them, you have to move them back to GPU memory. Okay, so that's the big challenge facing industry. Now, what is academia doing these days? Okay? Academia is approaching this problem from a totally different perspective. Academians are not thinking of KV cache as black box data. Now, in order to understand that, we have to look at KV cache from 3 levels of understanding. First of all, it is cacheable state. So if you cache it, you save cost. But at the same time, it is model's internal understanding. It's a semantic understanding. It's model's internal semantic and memory of the context. which means it has semantic meanings in it, and you can approximate any semantic data to make it smaller, to make it more reusable, as we will see in a minute. And more interestingly, this is actually what model uses to generate its output. Think about this. All the model, every token model generates only depends on two things. It's either the model weights or the KV cache. Essentially, mathematically, it's just a product of these two things. So KV cache can be changed to make inference even more accurate. You can change its output. So there are a lot of interesting things you can do about it. Essentially, KV cache shouldn't be viewed as just a black box tensor data that cannot be changed. It's AI native data that's manipulatable, that has values in itself. Okay? It's valuable data. And that's what we believe this is going to be the future big data. Now, research has been way ahead of industry in this space, by the way. People have been writing papers about this for the last 3 years, and we counted the papers on Google Scholar. There are 40x more papers published last year with KV cache in its titles, directly titles, than 2 years ago. It's a big literature, hot topic in research. But what are these researchers doing? They're producing a lot of ideas. Most of them are in these green parts. Okay? They are treating KV cache as very exciting semantic data. So it's an ML problem. Now, the bad news is industry cannot use them. There's so many research ideas and the industry are not using them because there's no good infra or open source project to deploy these algorithms and to deploy this algorithm in a production-ready way. Okay. Now, you may be asking, okay, Junchen, let me tell me a little bit about these research ideas. Okay. So I'm going to do that for the next few minutes to talk about two particular ideas that industry could readily benefit, and we're going to do that in our libraries too. So first of all, KV cache compression. Let's think about these two problems I said earlier. Industry is facing the problem of storing more KV cache cheaply and move KV cache fast enough between GPU and storage. KV cache compression solves both problems. KV cache compression makes each KV cache smaller so you can store more, and you can move them faster over the network, over low bandwidth networks. So how to do them? How to do KV cache compression? The basic idea of KV cache compression is quantization. Quantization uses fewer bits to encode each value in the KV cache tensors. Remember I said K-tensor and V-tensor, they are two big 3D tensors, number of tokens by number of layers by number of heads, big 3D tensors. Even with quantization, it's still going to be big 3D tensors. But the insight here is if you just want to store them over the network, store them in storage and send them over the network, you don't have to keep the 3D tensor shape at all, right? You can keep them in any bit stream. Essentially, you're encoding KV cache into bit streams like videos. Think about this. People never watch videos. People never store video in MP4 format in 3D tensors. Right? It's bit streams. People never stream videos over the network using 3D tensors. It's bit streams. Okay, so usually the workflow of a KV cache compression is like this. You have you do quantization, different KV cache quantization mechanisms out there. You probably have heard this thing called turbo quant. Turbo quant is one typical technique for KV cache quantization, there are good stories and bad stories about that, but it's a very typical technique for quantizing KV cache. But once you quantize it, there's still statistical properties you can leverage. And one property, for example, is the KV cache values of the same tokens can be very similar. Nearby tokens can be very similar, so you can just store their deltas, for example. Okay? So there are a lot of ideas like that. And finally, people do arithmetic coding, just like in video, to turn this structured data into bit streams. In research, there are papers, and from 3 years ago, this is a paper from 3 years ago, talking about 3 to 10x KV cache compression. You probably feel like, why am I discovering this today? This happened 3 years ago. And there are a lot of papers, and in fact, I strongly recommend any research students not to write papers in this space because they have to compare with 10 different baselines, at least. And there are a lot of common techniques. Now, it's good news for industry because this is matured literature out there. but there's no good platform for you to write these algorithms in a production-ready way. I'm going to go back to that in a second, okay? Because I want to talk about another research direction called KV cache blending. Now, what is KV cache blending? It's a totally different scenario. KV cache compression is to make each KV cache smaller, so you can store more of them. KV cache blending is to make each KV cache more reusable, can be reused in more scenarios. Now, first of all, let's think about what is not reusable. KV cache is not reusable if it's not in the prefix position. Here's a good example. If you ask the model to read a yellow document and a green document, their KV cache can be stored as prefix KV cache. But if the next time you want model to read these two documents jointly, and the model needs to understand these two documents. Now, ideally, you want to reuse these two KV cache so the model doesn't have to read these two documents again, right? Problem is, the first document's KV cache is reusable. The second document is not, because the KV cache was created, the green KV cache, the green cube was created when it was the prefix. And if you reuse it at a non-prefix position, the KV cache is not reusable because it doesn't have the cross-attention embedded between these two documents. The model essentially cannot jointly understand these two documents. Now, somehow, if you visualize the cross-attention matrix inside the model, you will see something like this. There are cross-attention between the tokens of these two documents. And if you naively concatenate the KV cache together, even if you solve the positional encoding, if you correct the positional encoding, the cross-attention is still not there. Now, good news here is if you look at the cross-attention on the left, not every token between these two documents have cross-attentions. Okay? Only a few tokens have strong cross-attention between them. And this is actually true with a lot of models these days. So a research idea here could be to dynamically identify these tokens to recover only the KV cache of these tokens. Now, this is in research literature. We have a paper, the first paper in this space, and there are also follow-up papers to do this. And the idea is very similar. Basically, you want to recover the cross-attention in a cheap way. So now let's go back to this slide. There's an exciting space ahead of industry because researchers have proposed all these ideas, but they haven't patented them. Okay? And industry can use it. Now, LMCache is a project to let people use these research ideas and want to bring research to production. So first of all, let's think about why it's hard for industry to use these ideas. What is the bottleneck? The bottleneck is actually most of the KV cache management software is either part of the inference engine or running inside the inference engine process. That is a big problem because anything you do there must involve the inference engine's process. And the inference engine is running at a super fast speed. Anyone who have looked at VLM or SGLang code will realize this. It's a fast-moving train. Anything you do there, anything you slow there, will slow the whole process down. It's very hard to do anything interesting, anything with respect to KV cache, such big data structure inside the inference engines. No. For example, they don't support rich interface for various KV cache operations. And anything you do about KV cache, loading them in and out, will incur significant overhead and slow down the inference. And finally, these engines are extremely hard to hack. And even if you hack them, there are probably hundreds of PRs in front of them to be reviewed by these projects. So all in all, doing things inside inference engine seems to be the standard, but that's holding back a lot of research ideas to be used in practice. Instead, LMCache recently had this major re-architecting. We run the KV cache management process outside the inference engine. So the inference engine doesn't have to, anything you do with KV cache doesn't have to touch the inference engine itself. Okay? So if you think about it from an architectural point of view, this is a major breakthrough. It's a major break from the traditional KV cache libraries because it completely decouples the KV cache management from the inference engines. It enables faster innovation, better compatibility, and better resource sharing. For example, one performance benefit of this is zero-copy CPU sharing. Imagine if you're sharing KV cache between two VRM instances. Used to be, you have to go through some sort of third-party KV cache pool. And even if you let the KV cache management libraries talk direct to each other, they reside in different VRM inference engines, right, instances. Okay? So there's still one extra copy between them. But with LMCache, the new multi-process mode, it has an independent layer that let VLM inference engines to share KV cache data with no extra copies. So this also is not just a performance benefit, it also gives us a much stronger and independent position in the ecosystem. With that independent KV cache layer, we can easily, it makes it much easier to integrate with various open source engines, including VLM, SGLang, and TensorRT, with various inference frameworks, and because they just need to run LMCache as a container. And of course, a lot of inference providers love that, and we integrate with both AMD and NVIDIA and other things. And finally, it's a great thing for storage vendors, because now when they write their integration of KV cache optimization, they don't have to touch the inference engine, right? They just need to interface with the KV cache library, LMCache. Now, LMCache is an open source project. We welcome everyone to contribute. This is just a grossly incomplete list of contributors from various industry partners. This is just people coming to our community, contributing their code within the first 2 months of 2026. So it's a incomplete list. There are a lot of companies behind this. I hate to say this, it's very hard to identify who contributed to the project. It's really detective work. It's not worth the best time of ourselves. Now, what's next? We want to build the best ecosystem of KV cache. And we're on the way to do that. And we're not just making incremental changes, we're making major architectural innovations. One thing here is to separate not just the LMCache library from the inference engine and storage vendors, but also separate LMCache core libraries from these plugins, which are basically algorithms and logics people can contribute. Okay, these libraries, these plugins in yellow, in orange, are things researchers can write. They can write their own plugin. They can write their own compression algorithm, for example. And we also welcome researchers and industry folks to write hooks inside LMCache to enable more plugins. So I'm at the end. This is the last slide. And everything I talked so far is either in LMCache or about to be available in LMCache. But more importantly, I hope this worth your time. It's the last talk, and I hope you'll see the future and get excited about it. Thank you.